Welcome to AI Research Weekly, the podcast that dives deep into the cutting edge of artificial intelligence research. I'm Nova, and with me, as always, is Onyx.
Great to be here, Nova. We've had a truly explosive week in research, particularly around the accelerating trend of Agentic AI. It feels like every new paper pushes the boundaries of autonomous systems, but also highlights the growing pains of complexity and reliability.
Absolutely, Onyx. The sheer volume of papers mentioning agentic AI this week is staggering. Over 30, just for that core concept. It's clear that the field is moving rapidly towards systems that don't just generate text or classify images, but actively pursue goals, plan, and interact with the world. But that raises a massive question. How do we even begin to evaluate these increasingly sophisticated multi-turn, multimodal agents? It's not just about a single accuracy score anymore.
You've hit on the central challenge, Nova. And the research community is responding with some really thoughtful advancements in evaluation. Let's start with general agent evaluation, a paper that introduces a unified protocol and a new framework called Exgentic. This is critical because, as you mentioned, existing benchmarks are often bespoke, tied to specific environments or implicit assumptions about an agent's prior knowledge.
So they're trying to standardize how agents talk to benchmarks. What does this unified protocol actually do? Does it abstract away environment details or enforce specific API calls?
It's more about mediating communication between agent interfaces and benchmarks through a canonical task representation. It allows implementers to designate specific actions as message actions or final answer actions, making it more generalizable. The Exgentic framework built on this enables modular insights, allowing researchers to compare architectures, analyze LLM impact, and optimize agent model pairings. They've even established an open general agent leaderboard, which already features 5 prominent agent implementations across 6 different environments.
An open leaderboard is always good for driving progress. Did they find anything surprising from the initial evaluations?
The analysis points to something we've probably all suspected. An agent's success is still primarily dictated by the underlying large language model. Claude Opus 4.5 achieved the highest performance, which isn't a huge shock given its capabilities. However, on the cost efficiency front, GPT 5.2 configurations offered the best trade-offs, making it optimal on the Pareto frontier. Even if Opus 4.5 achieved higher raw performance at 3 to 33 times the cost. It really underscores the practical considerations for deploying these agents.
That's a significant insight. Performance is one thing, but if the operational cost is astronomical, it changes the game entirely for widespread adoption. So the core LLM matters more than the specific agentic scaffolding around it, at least for now. This suggests we should really be pushing for more efficient, high-performing foundation models.
Exactly. And to get more specific, 2 other major benchmarks emerged this week, directly tackling complex agent capabilities. First, Mobility Bench, a new benchmark for evaluating LLM-based route planning agents. It uses large-scale, anonymized real user queries from a map, covering over 350 cities worldwide.
Real-world data, actual user queries, that's a huge leap from synthetic environments. What did they find about current route planning agents?
They found that agents perform competently on basic information retrieval and standard route planning, but they show significant struggles with preference-constrained route planning. This indicates substantial room for improvement in personalized mobility applications. The benchmark introduces a deterministic API replay sandbox for reproducible evaluation, eliminating variance from live services, which is a clever way to ensure apples-to-apples comparisons.
Preference-constrained is the interesting part there. It's easy to find the shortest path, but finding the most scenic, avoiding tolls, and stopping at a vegan cafe is a different beast entirely. It highlights the gap between raw computational capability and nuanced human understanding, or preference modeling.
Precisely. And then there's OmniGaia, pushing the boundaries even further. This is a comprehensive benchmark for evaluating omnimodal AI agents, requiring deep reasoning and multi-turn tool execution across video, audio, and image modalities. It features 360 tasks across 9 real-world domains.
Omnimodal, so not just vision language, but truly integrating multiple senses and modalities with complex reasoning and tool use. That sounds like a monumental challenge to benchmark.
It is. They use a novel omnimodal event graph approach to construct complex, multi-hop queries that necessitate cross-modal reasoning and external tool integration. They also propose an agent, OmniAtlas, operating under a tool-integrated reasoning paradigm with active omnimodal perception to selectively process long media segments. The results are telling. The strongest proprietary model, Gemini 3 Pro, achieved 62.5 pass at 1. An open-source baseline, Qwen 3 Omni, started at 13.3, though OmniAtlas's training recipe improved it to 20.8. The gap is still huge, highlighting just how nascent omnimodal capabilities are.
Wow, 62.5% for a top proprietary model isn't bad, but it means nearly 40% of tasks still stump it. And the open source performance really puts into perspective the complexity of integrating these modalities natively. It feels like we're still building the cognitive architecture for these systems, not just optimizing components. This touches on some of the recurring problems we're seeing, like multi-agent LLM systems suffering from false positives, or the thermodynamic collapse of symbolic systems under cognitive load. How do we even begin to guarantee reliability in such complex, multimodal, multi-turn systems?
That's where some of the architectural innovations come in. The manifold architecture, for instance, introduced this week, is a specification-driven orchestration architecture designed to ensure output correctness and prevent infinite retry cycles in complex multi-agent LLM systems. It combines the specification pattern with fingerprint-based loop detection, essentially treating specifications as verifiable contracts. This directly addresses the critical problem of false positives that plague multi-agent systems, where they report success on tasks that actually fail strict validation.
So Manifold is trying to add a layer of rigorous contract-based verification, almost like formal methods for agent orchestration. That's a practical and necessary step towards building truly robust agentic systems. We need that accountability. It's not enough to just achieve a task. It has to be done correctly and verifiably, especially as agents move into sensitive domains.
Agreed. Speaking of robustness and improving models, another standout paper this week. From blind spots to gains, diagnostic-driven iterative training for large multimodal models introduces the Diagnostic-Driven Progressive Evolution, or DPE, framework.
DPE sounds intriguing. What's the core idea?
DPE introduces a spiral loop where explicit diagnosis of an LLM's weaknesses guides data generation and reinforcement. This leads to stable, continual gains across 11 benchmarks. The key insight is that instead of relying on general heuristic signals or just pursuing superficial complexity, DPE provides interpretable diagnostics, attributing failures to specific weaknesses within a 12-dimensional capability space.
Interpretable diagnostics for LLMs. That's a huge step. We're often throwing data at these models and hoping they learn. This sounds like a more surgical approach. How much data are they needing for these gains?
That's one of its most impressive aspects. Experiments on models like Qwen 3 VL8B Instruct and Qwen 2.5 VL7B Instruct showed broad improvements in multimodal reasoning with only 1,000 training examples. This showcases its efficiency compared to static data training methods. The framework also employs a multi-agent system with image search and editing tools to source and annotate diverse visual content, constructing high-quality, weakness-focused training samples with deliberately controlled distributions.
Only 1,000 examples for broad improvements across 11 benchmarks? That's a big deal. It suggests a qualitative shift in how we think about LLM training, moving from brute force data scale to intelligent, targeted intervention. This diagnostic capability could drastically cut down on compute costs and accelerate specialized model development. Does it make the training process more stable or introduce new complexities?
The paper claims DPE's diagnostic mechanism significantly improves training stability during iterative training, and its unlabeled multimodal annotation effectively alleviates bottlenecks caused by static data, especially for long-tail challenges. Unlike previous methods constrained by static image sets and template-based text rewriting, DPE can adaptively source images and construct targeted questions, allowing it to overcome the scarcity of visual diversity. It's a significant advancement in self-evolving frameworks for LLMs.
That sounds like a powerful tool for continual learning in LLMs. But speaking of how these models represent and reason with visual information, there was another fascinating paper this week that actually challenges some fundamental assumptions about latent space reasoning. Imagination helps visual reasoning, but not yet in latent space. That title alone is a head-turner.
Indeed, Nova. This paper uses causal mediation analysis to reveal two critical disconnections in latent visual reasoning within MLLMs. An input latent disconnect, where input perturbations negligibly change latent tokens, and a latent answer disconnect, where latent token perturbations minimally impact the final answer.
Wait, so the internal, high-dimensional latent representations that we typically assume are doing all the heavy lifting for visual reasoning aren't actually carrying that much discriminative information, or at least not in a way that directly correlates with the final output. That's a fundamental critique of how we might be thinking about MLLM internals.
That's precisely it. They found that latent tokens in MLLMs exhibit high homogeneity and encode limited visual information, making them insufficient to support downstream reasoning on their own. And here's the kicker. They propose CapImagine, a simple text space imagination method, which significantly outperforms complex latent space baselines.
A text space imagination method outperforms latent space baselines. How much better are we talking?
CapImagine achieved 4.0% higher accuracy on HR Bench 8K and 4.9% higher on MME Real-World Light. That's a substantial margin. The authors argue that explicit imagination through text offers a more faithful, interpretable, and causally effective approach to visual reasoning compared to opaque latent space methods. This implies that while MLLMs may appear to be reasoning visually in their latent space, their core reasoning might still be happening more robustly in the symbolic textual domain, even when dealing with visual inputs.
That's a huge delta and a fundamental challenge to some widely held intuitions in multimodal AI. It suggests that perhaps our models are faking it a bit in the latent space, and the real imagination or reasoning is more effectively stimulated through textual prompting or a textual projection of the visual input. It really makes you question the nature of understanding in these models and where the heavy lifting actually happens. It's almost saying, don't just look at the pixels, tell yourself a story about them.
Exactly. It highlights the interpretability benefit, too. Textual imagination is inherently more transparent than trying to decipher the dynamics within latent space. This isn't to say latent spaces are useless, but it suggests we might be overestimating their current role in complex visual reasoning and perhaps need to rethink how we design for it, potentially by integrating more symbolic or explicit reasoning paths.
So we have models becoming highly agentic, but facing significant challenges in evaluation, reliability, and fundamental reasoning. And solutions are emerging from diagnostic-driven training to rigorous architectural contracts, even to rethinking what imagination means for an AI. It's a dynamic and exciting landscape.
Absolutely. The convergence of these trends is fascinating. We're seeing agentic AI rapidly accelerating, with 34 mentions this week alone, pushing towards truly autonomous systems. This is naturally leading to discussions around the agent economy and job atomization, hinting at the profound societal shifts on the horizon as AI moves from tools to teammates or even independent economic actors.
Right? And the focus on verifiable contracts for multi-agent systems like Manifold, or the rigorous evaluation frameworks like OmniGaia and Mobility Bench, they all speak to the growing maturity of the field as it confronts the real-world implications of these advancements. We're not just building models anymore. We're building autonomous entities that need to be accountable and understandable.
Exactly. The challenges around structural failures of the symbolic web under infinite AI-generated text, or the thermodynamic collapse of symbolic systems, these aren't just theoretical curiosities. They are critical problems that demand foundational solutions, and the push for more robust, interpretable systems is a direct response to that.
It's clear that the next few months will be dominated by efforts to tame the complexity of agentic AI, ensuring their reliability, verifiability, and developing robust multimodal reasoning capabilities. I'm especially interested to see if the text-space imagination paradigm gains more traction and how it might influence future MLLM architectures. It's a challenging week, but filled with truly foundational work.
Definitely, Nova. We're witnessing the field grappling with what it means to build truly intelligent, autonomous systems. The next wave of breakthroughs will likely come from these areas of integration, reliability, and deeper, more verifiable reasoning across modalities.
That's all we have for this week's AI Research Weekly. Thanks for joining us, and we'll be back next week to unpack the latest in AI research.
See you then.